Hello and welcome to the Richardson RFPD Tech Chat. My name is Michele Sclocchi and I'm the Field Application Engineer within Richardson RFPD Energy and Power Group. Today I'm joining in today's Tech Chat by Ashish Gokhale, a Product Line Manager for Power Product at Skyworks. Welcome, Ashish.
Thank you.
Today, Ashish and I will discuss the unique characteristic of GaN power FET. And we always get the few common questions from the design engineers that are approaching GaN in their power design that we would like to address during today's call. Gallium nitride technology is increasing its adoption in many different power converter applications. I know there is a short question and long answer, but in a nutshell, what's the most critical parameter for selecting an isolated driver for an eGaN type of application?
Okay. Yeah, absolutely. You're right about the GaN adoption being extremely fast in the marketplace. That's absolutely happening. And then the isolation portion of the gate driver becomes a critical piece of the puzzle for designers when we're talking about higher power applications, where let's say the DC link voltage is about 100 volts or so, or higher, of course. And that's when the safety requirements, the SELV safety requirements kick in, and isolation then becomes, part of the equation. So what do we look for when you look for an isolated gate driver? Is number one is the isolation ratings. They should be at a level that's higher than what you really require in the applications for guard band purposes. The other thing to look for would be that the driver has been proven in the field. So Skyworks drivers have been out there for more than 7 years or so. We have shipped about 500 million of them, and we have had absolutely zero DPPM for isolation fails. So these are field proven devices. Number two would be the transient immunity rating of the driver itself. It's usually specified as CMTI, or common mode transient immunity. And especially for isolated drivers, this is not a trivial performance characteristic. This has to be finely tuned in at the design stage, and for it to work properly for an isolated driver. For a non-isolated driver, it's also important, of course, but it's not as finicky to design in as it is for an isolated driver. So in any case, it is critical because the full benefits of the GaN device can really be realized when you're switching at a faster rate. A typical switch time could be, let's say, about 5 nanoseconds, and a typical DC link voltage, let's use a number 600 volts, not uncommon. So, which means that you get a slew rate when you're switching 0 to 600 volts in about 5 nanoseconds. That's about 120 volts per nanosecond. If the driver cannot withstand that kind of a high slew rate, then it can glitch. Glitching can cause two problems. Number one would be just you lower the efficiency, but because you're losing you lost pulses now, and therefore you're losing what you're designed in the modulation, and so that's loss of efficiency. Now you use GaN to increase the efficiency, so this would not be a good thing. The number two reason for having a good transient immunity rating is safety itself. Because if you cause the driver to falsely switch, and the driver turns on a power switch, again in the half bridge topology, for example, and it's on when it's supposed to be off, then you could have a shoot through condition, which is a big safety concern. So it's important from both of those angles. Number three would be suitable driver output levels. Uh, a lot of GaN, enhanced mode GaN FETs out there cannot sustain more than 5 or 6 volts on the gate. So they vary a little bit. So let's say about 6 to 7 volts would be the absolute max ratings. So the driver should be capable of fully turning on the GaN at 5 or 6 volts, depending on the manufacturer, but also have a UVLO level that's low enough, that's lower than those levels, so to have a safe operating area. So when it turns on to where the driver itself turns on from the UVLO stage, and when it turns the GaN fully on. So that little headroom there is important. So the UVLO has to be low enough. And for Skyworks drivers, we have a 3-volt UVLO level, which is absolutely perfect for driving these kind of GaN transistors. And last but not the least would be the timing characteristics. So we're talking about latency, jitter, as well as dead time specifications. So these specifications need to be tight as well as low as possible, by which I mean the delays and the jitter should be as low as possible. And they should be well matched from channel to channel if it's a dual driver or a half bridge driver, as well as from part to part, so that within systems you could have, a very consistent performance from part to part for the end system as well. So Skyworks drivers are actually the only drivers in the industry that have a jitter specification, and we spec a typical jitter about 200 picoseconds. So these are really well suited from all of these 4 characteristics that we just mentioned.
Thank you, Ashish. Since you explain very well, the time difference of, the importance of the correct timing with GaN. Let me ask you another question about the timing. Why that time is particularly important in a GaN switching application?
Yeah, that's a really good question. So dead time is important because that's one of the key things to optimize in the system to basically maximize efficiency of the system. So too short a dead time or too long a dead time doesn't work. And for typical GaN power switches, the dead time should be in the tens of nanoseconds. So about 50 nanoseconds would be typical number. In fact, as you can see here, 40 nanoseconds is the absolute optimum time to maximize efficiency. So so what the driver needs to have again is a very accurate characterization of its dead time, and also very low variation from again, as I mentioned before, channel to channel as well as from part to part. And Skyworks drivers have a dead time specification. You can tune it to as low as 20 nanoseconds, and it can go up from there all the way to hundreds of nanoseconds. So it's the perfect range for optimizing dead time on a GaN-based system.
Thank you. Let me just add another comment regarding that time. With GaN technology, we have a lot of design going on in Class D audio, and several customers point out that the dead time is very important to reduce the total harmonic distortion. I mean, to improve the performance, the audio performance of their amplifier. And Skyworks offer a family of driver well suitable for GaN that works very well with the Class D, short time, programmable, very low jitter, and that is very important in Class D.
Absolutely, yeah. That's a really good point. Yes.
The last question I would like to ask you is, we know that the main advantage of GaN, you get it at high switching frequency. So GaN can switch at the high switching frequency and while keeping a very good performance and efficiency. Typically, they try to go to in the megahertz range or even above, right? And most of the drivers today are specified at 500 kilohertz. Is there really a limitation, for the driver, or can we go higher than what usually is specified in the data sheet?
Yeah. Now that's a really incisive question. So I'm going to throw this graphic up, and we'll explain that in just a minute. But you're right. Usually drivers have some curve like this in the data sheet, or they have in the electrical specification tables. They might have, let's say, specify IDD, the switching current, for example, at 500 kilohertz. That is just a test point to take a data measurement. It doesn't necessarily imply that that is the limitation of the driver. And in fact, our drivers are very well capable of switching up to 5 megahertz or even higher. The real limitation is basically going to be how safely can you take the heat out when you're switching the driver and then the GaN FET at that kind of rate. So as you know, the power is going to go up as you increase the switching frequency. So what this curve is showing is basically the safe operating area for a particular switching frequency versus how much gate charge there is. What is the gate charge that you're driving with this isolated driver? And as you can imagine, as the gate charge goes up and the switching frequency has to go down to keep the power in the safe area. So that's what this curve is showing you. Now, if you notice, this is we're talking about, let's say, 2 microcoulombs here of gate charge, and then you can still safely switch to about 750 kilohertz. That's what this curve is showing you. Now, a typical gallium nitride gate charge, we're talking about nanocoulombs. So 5 to 10 nanocoulombs is pretty typical. So this is microcoulombs. You can extend the graph to the right if the gate charge is low enough. And you can very well switch very safely over megahertz frequency. 1 or 2 megahertz will be very safe. So again, it's going to depend on how good the thermal design is, and it's going to depend on what kind of gate charge it is that you're switching. But this is just a typical representation of what the driver can do, so that its maximum junction temperature is not exceeded. And that's really the point of the safe operating area. This only takes into account the thermal junction to ambient thermal resistance. So if you have other cooling mechanisms, or if your thermal design is really good, you can well exceed that. So bottom line, the driver itself can switch at a pretty high frequency. The only thing to be considered is what is the gate charge and what power dissipation can you estimate, and so that you don't exceed the maximum junction temperature. All the equations are in the data sheet for you to calculate what exactly it's going to look like. So you can calculate your thermal budget, your power budget, and then define your own safe operating area.
Thank you, Ashish, for explaining the importance of selecting the proper isolated driver for power GaN application. You can learn more about this and other topics by visiting the Knowledge Center of Energy and Power section of Richardson website, going at www.richardsonrfpd.com/EP, and select the topic of interest, ask to the expert, and submit any question. Thank you again, Ashish, and also thank you for you watching the tech chat of driving GaN devices.
Thank you very much, Michele.
Thank you.